Today we're going to be reviewing how to do the calculations for energy, including wavelength and frequency, Planck's constant, and the speed of light. What's really helpful before you get started is to know these three formulas, as well as how to use the EE button on your calculator. That's important. And also to use these steps in solving every problem. If you use these steps, it becomes very easy to make sure you get every problem correct. You may want to have your reference chart available, which is these formulas are on the back of your reference chart, and it helps to have the information about Planck's constant and the speed of light from your reference chart. So now we'll start. Most students, we did number one together in class, and we noticed that there's a wavelength here of 422 nanometers. It's important to label from English into whatever the term is or the symbol that you're using. This is talking about wavelength, and they want to know frequency. Well, whenever you look at your chart, you have a formula that says speed of light is equal to frequency times wavelength, but you'll have to rearrange the formula for frequency. And so you're going to divide both sides by wavelength, and so frequency is equal to the speed of light over wavelength. When you plug in the speed of light, which is meters per second, and then divide it by 422 nanometers, you also have to convert from meters to nanometers using the conversion here. 1 nanometer is 10 to the negative ninth meters. When you complete all of that in your calculator, you get 7.11 times 10 to the 14th hertz. Be sure you show all your work. There are 3 significant digits. When you go to the energy, what is the energy of a quantum? And so that's in the symbol of E with a frequency of this, so this is equal to F. So you want to find a formula that has energy and frequency in it. And whenever you look at your chart, you'll see that the formula that has energy and frequency is this formula, and it uses Planck's constant. So energy is equal to Planck's constant times frequency. Okay, so you'll use Planck's constant here, and then your frequency is here. Please keep in mind that hertz is the same thing as 1 over second. So whenever you're writing in this number, you might want to put in 7.39 per seconds, because that would be helpful. When you finish, your energy is equal to 4.90 times 10 to the negative 19th joules. Be sure that your answer is in joules. This next one has a radiation of 1.2 centimeters. This number is actually wavelength. Okay, and they want to know what is the energy, so they're looking for energy. So when you look at your formulas, you'll want to use the formula that has energy and wavelength. It uses Planck's constant and the speed of light, and so you'll use that formula. Energy is equal to Planck's constant times the speed of light over wavelength. Please keep in mind that this is in centimeters, so you'll also have to have a conversion from centimeters to meters. So when you're done, you will get an energy of 1.66 times 10 to the negative 23rd joules. All right, let's do the next one. Calculate the wavelength of KTRH in Houston, or KTRX, and it has this particular frequency. So they want to know the wavelength, so that's this symbol, and this is a frequency. So we want to find a formula that has frequency and wavelength in the same formula. Here is the formula that I would use, and it includes the speed of light. But you need to rearrange the formula. So this is what the original formula is. Whenever you use algebra, you divide both sides by frequency. So you get wavelength is equal to the speed of light over frequency. And so we know that the speed of light is 3.00 times 10 to the 8th meters per second. Okay, and we know that frequency is this many megahertz, or you could put it down here, or you could put it over here. It doesn't really matter, because they're both in the denominator. Now, remember before I said that hertz is equal to 1/2. So if I were to put hertz in here, it's the same thing as this number over seconds, 1/2. So my seconds cancel, and I end up with meters. So when I put that in my calculator, let's just practice that for a moment. When you're using your calculator, you want to know where the EE button is right here, so that becomes very important. EE stands for everything that's not the base or the exponent, so it's times 10 to the. So when I'm typing in the speed of light, 3 second EE, 8, so that's 3 times 10 to the 8th, it's going to look like this. This is the same as 3 times 10 to the 8th. Then I'm going to take the speed of light, and I'm going to divide it by this number. So divided by 1, 0, 0, 7, 0, 0, 0, 0, 0. Okay. Then when I get my answer, I get this really long answer. So I want to go back. That's calculator vomit. I looked at there's 3 sig figs here, and over here there were 4 sig figs. So the least number of 3 and 4 is 3. So I look over to my fourth one. The 9 tells the 7 that he has to round up. So my answer is 2.98 meters. Don't forget your units. That's really important. Okay. Number 5 talks about diamonds. Some diamonds appear yellow because they have this frequency. So this number is frequency. They want to know the wavelength. So we're looking for wavelength. So we're looking for a formula that has frequency and wavelength in the formula. Well, we just used that one. It's right up here. Okay. So we just did that. Wavelength is equal to the speed of light over frequency. And this is hertz, which is 1/2. So when you're done, you get 4.15 times 10 to the -7th meters. Be sure to show all your work. I'm just not showing it because that's something you need to practice yourself. All right, what is the energy of a photon? So we're looking for energy corresponding to radio waves frequency. So here's my frequency. Remember, per second is equal to hertz, which is equal to 1/2. So they're all the same. So now I'm looking for a formula that has energy and frequency in it. When I look at my chart, energy is equal to Planck's constant times frequency. So you're going to take this number and multiply it by Planck's constant. And whenever you're done, you're going to have to round it to 4 significant digits. 9.044 times 10 to the -8 joules, and that's energy. In order for an electron to be ejected from a cesium atom, this much energy, so this number is energy, so I have energy here, and they want to know the wavelength, so I need a formula that has energy and wavelength. Well, energy is equal to Planck's constant times speed of light over wavelength, but I need to rearrange it, right, because I'm looking for wavelength. So I'm going to multiply this side times wavelength and this side times wavelength. These cancel. Now I need to divide this side by energy and divide this side by energy to get rid of my e's because I want wavelength alone. So my formula becomes wavelength is hc over E. So when I put in my Planck's constant and my speed of light and I divide it by my energy, I get 1.29 times 10 to the -6 meters, or 1.29 micrometers, because micro is 10 to the -6. Okay, let's look at number 8. Number 8 talks about which one of these photons has the highest frequency. So I'm looking for F. Photon 1 has energy. So photon 1, I need to have a formula that has energy and frequency in it. And that would be this one. Energy is equal to HF. And I'll have to rearrange that for frequency. So I got to divide by H. And so frequency is equal to energy over here. Now my photon 2, they gave you wavelength, okay, which is this. So photon 2, I'm going to use a different formula to solve for frequency. So I have the speed of light is equal to the frequency times lambda. So when I want to solve for frequency, I divide both sides by lambda, and I get frequency is equal to speed of light over lambda. So both of these are going to solve for frequency, and then I'll compare them. So photon 1 has an energy of 1.7 times 10 to the negative 17th joules, okay? And I need to divide that by Planck's constant, so 6.63 times 10 to the negative 34 joules and seconds. That's the units. So my joules will cancel, and so I'll get a frequency in hertz, which is good because per second and hertz are the same thing. Now remember how to type that in your calculator. The 1.7 times 10 to the negative 17 is going to be 1.7 second EE negative 17. Okay, and so it looks like that. Hold on. 1.7 second negative 14. So it looks like this. Okay, and I'm going to take that number and I'm going to divide it by Planck's constant. So divided by 6.63 times 10 to the negative 34. 6.63 times 10 to the negative 34. Okay, and then whenever I get the answer, I round it, and so I get 2.6 times 10 to the 16th hertz, or per second. When I do my second frequency, I take the speed of light, which is 3 times 10 to the 8th, and divide it by the lambda, which is up here, 3.9 times 10 to the negative 9, and I get 7.7 times 10 to the 16th hertz. Now when you look at this one, 7 to the, both of these have the same exponent, so we're talking about the same number of zeros. So 7.7 is larger than 2.6. They want to know the highest frequency. The answer is photon number 2. Okay. A flame test is done. We did that in the lab. We have a wavelength here. What is the energy of the photon? So my formula is going to be this formula. So when I type in Planck's constant, speed of light, and then I divide it by this, I get that the energy is 4.03 times 10 to the negative 19th joules. Check your work. An atom releases a photon of a wavelength. This is wavelength. How much energy? Again, you're going to use the same formula as you did up here. So energy is equal to Planck's constant, speed of light over wavelength. And when you type it in your calculator for number 10, you get 2.15 times 10 to the negative 19th joules. The very last one, and then we're done, is the blue-violet flame test. This has a wavelength of 451 nanometers. Obtain the energy. So here we go. We're using the same formula as above. And when you type it into your calculator, don't forget that this is nanometers, okay? So there's 10 to the negative 9th meters in a nanometer, okay? So be sure to put that conversion in there. And the energy you'll get is 4.41 times 10 to the negative 19th joules. Now you can check your work. Good luck.